2005 question 5b, collisions. So this question is a question on oblique collisions, and I would strongly recommend for oblique collision questions to follow the following steps, which are nearly always the same, and those steps can be derived from this word to test. Diagram, D for diagram, table, equations. Equations we mean are of course the principle of conservation of linear momentum and Newton's experimental law. Solve the equations, and finally there's nearly always a little bit of trigonometry to be done at the end. So let's apply these steps to this question and see how far they take us. So the first step is to draw a diagram, and here I would recommend redrawing the diagram if it's already given to you, or if not, drawing your own new diagram. But draw it without the spheres, because we're just interested really in the trigonometry behind this diagram. So let's have a quick look. The diagram is shown here, and we have two spheres, and this is the important line to draw first. It's the line joined their centres. The line joined their centres, always without exception, is your x-axis. So that's the first thing we'll draw. So question 5, 2005. Part B, we'll draw this line, and as I said, this line represents the line joining their two centres. Let's just dot those two centres, first one and the second one here. And in the question we're told the first sphere came in at an angle of 45, like this, as did the second sphere. And just to emphasize, this is our x-axis for the remainder of the question. In our x-axis also. And first we need to do is, of course, when you have an x-axis, you have to resolve along that axis all forces and directions and so on along that axis. In this case it's velocities. So let's take our vector u here and resolve it. So resolve on the side over here. Parallel to x, parallel to y. That's u, and that's 45. Well, this must be u cos 45, or u over root 2. And this is u sine 45, also u over root 2. And by symmetry, the other one will have the same lengths on the sides, u over root 2. So that's our first step, done the diagram. Next we will move on to a table. And the table looks like this. We want to have 3 columns. And we'll give them 3 titles: before the collision, and after the collision, and the mass in the middle. So the first thing is the mass, and we're told in the question that the mass of A is m, and B is an identical sphere. So we'll put those in for A and B. And the next thing we do is we resolve in terms of I and j. So x corresponds to our I vector, and if you look at u coming in here, we see that it's u over root 2 along I, plus also u over root 2 in the j direction, or the y direction. And by symmetry, the magnitudes are the same for this vector. Now, we have to be careful though with this guy, because if you resolve this u, there will be a component. Actually, let's show it just to be absolutely sure. Let's click the resolve down here. So these arrows are very important to show the direction. So it's u in that direction, and this is u over root 2, and u over root 2 again. But if you look at this arrow, watch this carefully, this arrow is going in the minus x direction or the minus I direction. So that's a minus u over root 2 in the I direction. And it's still plus in the j direction, however. This is plus, so it's plus u over root 2j. Now, for the velocities after the collision, we need to take account of the impact itself. And let's go back to the diagram for a sec. And the important thing to realize here is when two spheres collide, the impact is at this point only. It's the point where the two spheres meet. And the force, because of that impact, is only along this axis. So the impact only acts along that line. Newton's third law, equal and opposite forces along that line. This means there is no force in the j direction. And if there is no force in the j direction, by Newton's first law, that means that there is no change in velocity in the j direction. And in this allows us in our table then to use the same j part after the collision, because there is no force in the j direction, therefore in the j direction the velocity hasn't changed. So in the j direction we can always use the same speed, u over root 2, the same component, u over root 2j, and u over root 2j down here. And we don't know what it is in the I direction afterwards, so we just call it something, just give it a name, call it P in the I direction. And maybe call this one Q in the I direction. And the next thing I would do is highlight the I part only in all of these. Because the I direction is the I direction where all the interesting stuff is happening. This is where we have to do all our calculations. And that's step 2 done. That's our table finished. Now we're on to the equations. So the equations we're talking about are, of course, the principle of conservation of linear momentum in the I direction. That's m1u1 plus m2u2 equals m1v1 plus m2v2. And the key thing here is only to apply this along the x direction or along the I direction, because that's the I direction where things are changing. And that's why I've highlighted in green, so we can just fill directly into this equation. Now, well, the masses are the same before and after, m and m, so we can just cancel all the m's straight away in this particular question. So m just goes straight away, and u1 is u over root 2 plus u2. Again, be careful, these are all vectors. It's a minus. It's minus u over root 2 is equal to v1, which is p, plus v2, which is q. These cancel nearly with naught on the left hand side of the equation. Naught is equal to p plus q. And this is your first of two simultaneous equations. We label it number 1.